All right, folks, welcome back for our 2026 series of PRIMA Community Astronomy Science and Technology Talks. So before we get into our talk today, I wanted to give just a really brief update. So great news. So the concept study report submission deadline is almost here. So the concept study reports are due to NASA on January 29th. So the PRIMA team is very excited to have finished the massive CSR document. And so that will be submitted. And then the next step is looking forward to the PRIMA site visit, which will be happening at JPL in May 2026. And so we really just want to give a huge thank you to everyone in the community, folks who gave us input, folks who've written papers about or even mentioning PRIMA, folks who did the effort of writing science cases for both the first and second General Observer book, and then everyone who has just been supporting and talking about PRIMA. It's really great. There was a wonderful turnout and enthusiasm at the January AAS. We're also looking forward to being present at the summer AAS in Pasadena. Keep in touch. We will be sharing more information as we get the concept study report actually submitted and keep moving on, hopefully into the next phase and phases beyond that. So upcoming, we have several more talks, and we're planning to be continuing this talk series throughout the year. So in February, we will have a talk from Susan Clark at Stanford, and in March, we'll have a talk from Becca Levy at Space Telescope. But today, of course, everyone's here to hear from Meredith MacGregor, one of our PRIMA affiliates, and she'll be talking about really exciting that can be done with science that can be done with PRIMA on debris disks, as well as talking about a really exciting student collaboration idea that she has been helping lead with others on the team. All right, so go ahead. Let me stop sharing and go ahead, Meredith.
Okay. Let me get this up. Okay, so hopefully we can see this.
Looks great.
Okay, good. Move things around so it's not hidden on my side of the screen. Okay, so it's really great to be here and get a chance to share this with you. I will apologize in advance if a toddler busts in. We have gotten 15 inches of snow in Maryland, so we are totally snowed in, which means there's no daycare. So I have a 1.5-year-old running around my house. Okay, so I have basically divided this talk into two parts. I wanted to start off by talking about the debris disk science that we had a working group on debris disks for PRIMA, and I wanted to kind of overview what we could do with PRIMA and what we came up with from that working group, and then sort of end that part and then spend the rest of the time talking about the PRIMA Internship Program. Okay. So just as an introduction, so we're all on the same page, how do stars and planetary systems form? So we start from this sort of molecular cloud phase up here at the top, and hopefully you can actually see my mouse. Pieces of that cloud become overdense and they collapse to form new stars, and then those stars are surrounded by disks of gas and dust. Initially, these are, fairly massive disks, and this is what we call the protoplanetary disk phase, where we think there's enough material to actually form things like giant planets. Somewhere between, a few to 10 million years, most of the material in these disks is cleared, and what we're left with is our main sequence star, any planets that formed during that earlier phase, and this sort of remnant belt of asteroids and comets that we call a debris disk. So you can, think of this as like our planetary system, right? We have multiple debris disks in our solar system. We have the asteroid belt, the Kuiper belt. We have the Oort cloud. We have quite a bit of remnant debris. Okay, so just to draw the distinction between those two things more clearly, on the left side here are protoplanetary disks. These are all images taken from the D-SHARP survey with ALMA. So these are pre-main sequence stars. They're rich in this primordial gaseous material. This is sort of the reservoirs for planet formation. And on the right are debris disks, again, images taken with ALMA. These are now main sequence stars. there is actually gas, and we'll talk about that a bit. We think that that gas is likely coming from cometary collisions. So these remnant bodies in these disks are things like comets that are colliding and grinding to produce smaller dust grains and also outgassing. There's some thought that you could have ongoing terrestrial planet formation in these systems, but I sort of like to call debris disks the fossil record of planet formation in that, their composition and their structure sort of encodes what happened earlier in the planetary evolution process. Okay, so why do we care about debris disks? I highlighted two things here, and these are two things that I kind of dug out because they're kind of the themes of what we came up with as a working group. So, debris disks really give us clues as to kind of the origins of planetary systems. One way that they can do this is because any planets that are actually orbiting within the disk can gravitationally perturb that disk, and, create a bunch of structure, things like rings or clumps or eccentricities. They can carve out sharp edges. An example of this is what's here, which is kind of a small plot showing the distribution of Kuiper belt objects. And if you look at the classical and resonant populations, they're confined between two orbital resonances with Neptune. And that is seen as evidence of Neptune actually migrating outwards early in the solar system and basically, snow plowing all of those Kuiper belt objects into this resonant population. The other kind of thing that's interesting here is to look about how we can understand sort of the reservoirs for planet formation. You imagine you have planets forming in this protoplanetary disk. There's sort of two options. They could either, actually mix the material in the disk. Basically, as they migrate and move, they could stir up the disk and move material that we might only see in the outer disk inwards. Or they could actually potentially open gaps and separate that circumstellar material and create sort of separate reservoirs. And this would then presumably be traced into planetary compositions. So in this view, right, debris disks are sort of our laboratory for understanding how our solar system fits into exoplanetary systems, right? Is the architecture and evolution of our solar system common or rare? Okay. So how do we actually typically observe debris disks? You can look at them at essentially any wavelength you want. Different wavelengths are tracing a few different things. So they're tracing different sized dust grains and tracing different emission properties of those dust grains. So in sort of the optical through the near infrared, you're actually seeing scattered light. So these are small micron-sized dust grains that are actually scattering the light from the star. And that's what's shown in this top image here. This is a sphere image taken in the near IR, showing these waves in the AU-MIC debris disk system. And then once you move outwards in wavelength to like the mid-infrared through the radio, you're actually seeing thermal emission from dust. And that's what's on the bottom panels here. These are all images of AU-MIC, and the bottom are showing Herschel, ALMA, and the VLA, so moving from 70 microns out to about a centimeter. And to kind of get at that grain size distribution thing a bit, I stated that we're seeing different size grains and different emission processes. So if you plot basically the emission efficiency Q of a grain as a function of wavelength, at any given wavelength, the large grains that are about the same size as the wavelength are actually the most efficient emitters. So you can, pick any wavelength here, and whichever grain size matches that wavelength is basically dominating your emission. So you can sort of think of it as observing wavelength is roughly grain size. And then, this is looking at sort of the global distribution of dust grains in the disk. The number of grains as a function of grain size in this logarithmic plot essentially follows a power law. This means that, as perhaps expected, there are many, many more small grains. And when you put all of these things together, essentially it means that if we measure the flux density at any particular wavelength, we're actually tracing this grain size distribution, right? So when we look at this plot then, and we go from wavelength to wavelength to wavelength, this is tracing micron size grains, now 70 micron size grains, millimeter grains, and centimeter grains. So we're really getting, a picture of these disks now that are resolved spatially and also then in wavelength space and grain size. Okay, so there's been a tremendous growth in like planet formation research in the last decade and some change. And a lot of that is because we have amazing new facilities, right? So, on the left here is ALMA, which I'm sure most of you are familiar, right? But this is our amazing interferometer with 66 antennas spread out over up to 16 kilometers in the Atacama Desert in Chile. And then, now we also have JWST. So I always like to show this, back and forth plot, which is showing images of debris disks taken in the submillimeter and millimeter before we had ALMA. This was sort of the state of disks as I was just starting my PhD work. There's some interesting rings and structure, but there's a lot of blobs. And these are now new images that there was a press release that came out just last week on the ARCS collaboration that Seba Marino was leading. These are now the D-sharp survey equivalent, but for debris disks. So, you can go from looking at these same disks that don't look that particularly interesting to these amazing new images showing all sorts of rings and structures and things that we can really start digging into. Okay. So I just wanted to kind of highlight some of the interesting things we've learned about debris disks by going through a few individual systems and then kind of use that to motivate why we need PRIMA and then highlight all of the interesting science cases we have written as a working group. So, one debris disk system that we have studied a whole ton is Fomalhaut, largely because it's extremely extended on the sky because it's nearby. And so we can take extremely high resolution images. And Fomalhaut was famous initially because, it had this beautiful Hubble image and there was a detection of a potential protoplanet here that's marked as Fomalhaut B, which was thought to be carving out this eccentric ring. Then it looked like its orbit was a bit odd, so perhaps it's still a planet, but it's not actually carving this out. Then there's been subsequent papers that show that this is actually a collisional dust clump that's now disappeared. So, it's been a frequently studied system. And we looked at it with ALMA back in 2017 and got this really nice image showing this kind of clear eccentric ring. We've detected the star, so you can see that the star is actually visibly offset from the center of the disk. And then we went back and got even higher resolution data, and this was published by my PhD student, Jay Chidi, in kind of end of last year. So what can we do now with this sort of data? So this is a different way of looking at the disk structure. It's basically taking a cut across the disk. So this is flux as a function of radius, and it's taking a cut towards what we call the pericenter side, which is the side of the disk closest to the star, and then the apicenter side, which is the side of the disk farthest from the star, right? So this is pericenter here, and this is apicenter up here. And this is showing the data, which is the solid line, some modeling results, which are the various dashed lines, and then actually the JWST data for Fomalhaut as well, which is then this blue axis here. So some interesting things, right? The apicenter side of the disk here is significantly brighter than the pericenter side of the disk. You can see this flux difference. Surprisingly, the apicenter side of the disk is also significantly narrower than the pericenter side. So you can see this is about 12 astronomical units, and the pericenter side is about 16 astronomical units. And they actually have a different kind of gradient or slope to the inner edge of the disk. So we were basically trying to understand, what physically is happening in the disk, what kind of planet could be inside of this disk to actually create this structure. As you can see, our sort of simple models don't do very well. So these are the models that Jay put in his paper, and are those dashed lines there, where we're essentially have a pretty simple model where we have a forced eccentricity and the orbits are nested, so they have a pinching at the pericenter point, which does not match this data because the pericenter point is much wider. And so you can see these are the models and these are the residuals, and we have these like big negative and big positive residuals. Josh Lovell published a paper at the same time. So these papers came out together, adding in an eccentricity gradient, where actually the eccentricity of the disk varies as a function of the radius. So it starts off more eccentric on the inner edge of the disk and then gradually tapers off. And you can see that in this kind of more complicated model, actually, we do a better job fitting the data. So we've gotten to the point, with ALMA, my take-home point here, right, is that we've got such high resolution data that we can really be getting into the dynamics of these disks and trying to understand exactly what kind of planets could be shaping the structure. The other thing I wanted to highlight is, briefly, ALMA has also made an enormous advance in sort of looking at the cold molecular gas, both in debris disks and in earlier protoplanetary disks. So the left images here came out of the ARCS papers that were just published. So these are 6 debris disks detected in CO. So we can see now the structure both in CO gas and also in dust. And then the right image here is actually showing protoplanetary disks, and these are in a whole bunch of different molecules. These came from the MAPS collaboration with ALMA. So each row here is a disk, and then each column is a different molecule traced in that disk. With JWST, we're adding complementary information now. So one of the really notable things to me, I think, in the JWST studies is that they've gone back and looked at all of these kind of famous debris disks, and they're detecting this population of warm inner disks, which we did not know were there. So this is Fomalhaut, right? Here's that outer belt that I was showing you with ALMA, and then there's this actually, considerable intermediate belt that's highlighted here. This is with Vega, which shows the same sort of thing. It has an outer belt, and then it actually has this significant inner disk. So JWST is really letting us probe that sort of warm material that's much closer to the star. Interestingly, we might also see this in ALMA, but have missed it, and it's very hard to image because, we're sensitive to colder stuff with ALMA. But this is some new stuff that Jay has been working on, basically combining all of the ALMA data that has been taken on Fomalhaut across 3 different bands and actually using some new imaging techniques to image it all together. And this is overlaying the ALMA contours on the JWST data, and we actually see something potentially significant that overlaps with the intermediate belt. So that's maybe interesting because depending upon whether we see only small grains or only big grains gives us information about, what is the origin of these sort of intermediate disks that we, were missing previously. Okay, so that is a sort of brief overview of like a few things that I think are interesting in how we study debris disks. And what I want to do now is transition into why we need the far infrared. So this graphic is complicated, and that's sort of the point. On the left, it's showing a protoplanetary disk, and on the right, it's showing a debris disk. So you can sort of see the different grain populations and different temperatures and sizes. You can see the flaring in the protoplanetary disk. You can see the changes in composition in CO, in the grains and the gas as things are frozen out onto dust grains. And on the debris disk side, we see these sorts of comets that are potentially falling into the star. We have warm dust, we have warmed planets, and this kind of cold material. And here on the top are showing essentially like the radial areas that we can probe with these different facilities, right? So with ALMA, we're really sensitive mostly to this cold population out here. And with JWST, we're really sensitive to the things in here. And there's this big gap where we are actually, missing critical information, both in this sort of range of grain sizes in between things that are like 10 microns and a millimeter, in temperature space. And, this is why having something in the far infrared opens up a whole range of new science cases, because it, fills in this gap and lets us actually look at the entire disk, from the inner radius out to the outer radius, and this kind of intermediate range of grain sizes. So I am not going to go into the details of PRIMA because everybody knows this because you're on this talk, but just to sort of highlight one other thing that I'll mention kind of briefly. There's another mission that I'm involved in called POEM, which is actually doing some complementary and similar science and is a balloon, so will launch much sooner than PRIMA. And so from a planet formation perspective, POEM has a lot of, strength in planet formation, and it's kind of a nice complement in that it has higher spectral resolution and is also a little bit of a pathfinder in that it will let us look at some of these systems earlier before we get PRIMA so that we can, make better use of the time with PRIMA when it comes along. So I just wanted to sort of highlight POEM because I'm going to flash it up a couple of times. But, the main takeaways are that it's a balloon with a low resolution mode and 2 high resolution channels. And the high resolution channels, are targeted at about 112 microns and like around 40 to 60 microns with an R of about 100,000 and 50,000. Okay. So I mentioned this at the beginning, but as part of, the concept study report and this, the PRIMA team put together a new general observer science book, which was volume 2, and it had an enormous number of science cases submitted. I co-led a working group on debris disk with Christine Chen, who's at Space Telescope, and this is my consolidated list of all of the science cases that we put in on debris disks. So there are 9 of them. I was especially proud of this because there were 0 debris disk science cases submitted to GeoBook Volume 1. So we went from 0 to 9, really highlighting that there is a lot of really exciting science to do in these sort of more evolved planetary systems. And what I want to do basically is kind of walk through on the next several slides each of these science cases and why they're exciting and what we could do with PRIMA. So I'll start with the one that I led, and Gianni Cataldi also put in one. So there's actually 2, which should emphasize how exciting this is, science cases on measuring C to O ratios in debris disks. So here our goal was to basically use the high resolution mode of PHI-RES with the 63 micron and 158 micron lines of O1 and C2. And the goal here is to basically measure oxygen and carbon and compare it with the CO measurements that have been done with ALMA. Why is this exciting? So there has been, with JWST, a lot of effort to actually measure C to O ratios of exoplanet atmospheres. And there is this kind of tentative dichotomy between the directly imaged, really massive planets that have C to O ratios more like the sun, and the sort of closer in transiting exoplanets that really show a wider range. And there's been a lot of debate in the exoplanet community about, whether this points to something in how these different types of planets form. But part of the problem in actually doing that interpretation is that we don't really have ground truth measurements in disks to compare to. And so that's kind of the goal here. What I'm showing in the histogram is the blue and the purple are actual detections of O1 and C2 in debris disks to date. Those were all done with Herschel. You can see there's really only a handful, 4 or 5. And in gray are all the targets that we would expect to get with PRIMA. So this is making, an enormous increase in the sample size. And then this plot on the bottom is really showing those targets in a different way. It's showing the dust mass as a function of CO mass. So the measured CO mass from ALMA, and then the dust mass as again measured from ALMA. Okay, so highlighting how we can do this in a more, so the goal here with PRIMA is to really do a population level survey, right? Now, we can also look at this for individual systems. And one that is particularly interesting is Beta Pic. Beta Pic has been imaged like Fomalhaut many times. And what's shown here on the top is the Hubble image in the blue, the ALMA continuum dust emission in this sort of like paint green, the CO emission from ALMA in the pink, and then JWST. And the one big thing that's noticeable here is the disk is very asymmetric. The dust is asymmetric. There's this sort of funky cat's tail in the JWST image. There's a distinct clump of CO. And with this system, we can combine all of the data that exists because it's been observed so many times and really get a self-consistent look at, carbon monoxide, O1, C1, C2, and then be able to really look at the dynamics of the system. Now, PRIMA doesn't necessarily have the spectral resolution to do this entirely, which is why I wanted to bring up POEM as well, because with that, 50,000 to 100,000 resolution, we can actually use line tomography where we actually resolve the spectral lines to get at the dynamics. And since this will come first, we'll be able to do this really detailed study for beta PIC and then apply that knowledge to the larger surveys that we end up doing with PRIMA. Okay, then there were a number of science cases that were put in through a working group to really look for new debris disks and try and actually understand the population statistics of disks. So I split them into two categories. The first is what I'm calling unbiased disk surveys. So David Wilner and Carl Stapelfelt both led a case on this. They were slightly different. David's was to do a volume limited, so look within 10 parsecs at all of the sun-like star debris disks. And Carl actually was signing on to this all-sky survey that was proposed in some other science cases for PRIMA, and basically doing the statistics for what we could get from an all-sky survey in debris disks. Both of these are using the Primager, so not the spectroscopic modes. This image is showing kind of the spectral energy distribution for a debris disk, really highlighting that it peaks in the far infrared. So if you want to go hunting for debris disks, the far infrared is kind of the ideal wavelength to do that. And then this is showing the sensitivity curves in disk luminosity for some of the Primager modes and comparing that to what Herschel was able to do with PACS. And notably, this red point is showing where our Kuiper belt is. So one of the, Herschel did this. It did surveys for debris disks around nearby stars. But because it was limited in sensitivity, it is still, at least an order of magnitude, if not more, above where our own Kuiper belt is. So we actually don't have statistics on how kind of common debris disks that are the mass of our Kuiper belt are. So really doing these sorts of surveys would, really improve our understanding of these planet formation populations. How long do they persist? What fractions of stars have them? And actually be able to put our own Kuiper belt into context for the first time. The other two to highlight here are sort of different flavors of this, which is doing similar disk surveys, but focusing on maybe not just volume limited or all sky, but on specific host star properties. So Josh Lovell put in a science case to try and target young clusters because we actually don't have particularly good statistics on sort of the transition in between protoplanetary disks and debris disks. So trying to actually look at those, really toddler systems, let's say, that are growing up from being protoplanetary disks into debris disks. And then Patricia Lupe put in one to look at specifically M dwarfs, because a place that Herschel really did quite poorly in statistics is M dwarfs. So this is the sample of M dwarfs that she was proposing to look at. And these is another one of these sensitivity curves. But here you can see where all the M dwarfs lie and where the sensitivity is for PRIMA and where Herschel was. So Herschel essentially just, completely missed all of these disks. So this would really fill in some missing pieces as well. And just to drive that point home, Herschel's debris survey detected actually just 2 M-dwarf debris disks in a sample of 94 stars. And so this is the plot from Jean-François Lestrande's paper that just came out in 2025, showing the fractional dust luminosity completeness, basically, for PACS. And these are the 2 detected disks. So, this M-dwarf sample is about 10 times shallower than the comparable Herschel samples for sun-like stars. And, it would be very easy, as this is showing, to just, completely do worlds better with PRIMA. Okay. Christine Chen led a science case that was focused on looking at volatile ices in debris disks. So this is going back to the PHI-RES high resolution modes, really trying to target the 43 micron crystalline water ice feature. These are models showing flux density a function of wavelength for beta PIC and HD 181327. And these are the points from PAX from Herschel. So, in our solar system, Kuiper belt objects are rich in water ice and other volatile ices. And so, we think that played an important role in the formation of the giant planets. And we really don't have data on this in other planetary systems. Without something in the far infrared, we don't have the ability to really probe cold water for a very large sample of disks. So this is a big goal for POEM and then for PRIMA as well, to really do these sort of large-scale surveys for volatile ices. To prove that we really do expect to see something, this was a paper that Christine and her postdoc Chen Xi put out last year, showing the HD 181327 system with JWST, and they actually detected a feature of water ice at 3 microns, and it actually has a Fresnel peak in it at 3.1 microns. So this is showing this feature of water ice, and there's actually changes in the spectrum as a function of radius. So this was a really cool result out of JWST. But again, really for most of these systems, it's that 43 micron line that will be the most useful in terms of actually looking at cold water content. So another thing that has been, interesting and not particularly well understood is this population of what we call extreme debris disks. So these are debris disks that are flagged for having large changes in their infrared fluxes. Okay, so by large changes, I mean that the infrared flux is going up by, factors of many on short periods of time. And that has generally been thought to be due to kind of a really active collisional population, where some massive collision has happened in this disk and it's created this huge bump in the infrared brightness. Interestingly, these disks also show evidence for transiting exocomets, okay? Which means that we see transiting exocomets when larger bodies are kicked through collisions in towards the star and they actually transit in front of the star. So this is showing an example of that from a system called RZ Pisces, which is one of these extreme debris disks. These are test-like curves from a paper that was actually published by an undergrad working with me, Adeline Gibson. And you can see just all of the dips that are happening in this like curve. So we still don't, fully understand these systems. And so John T. Marshall put in a case to use Primager to actually map these extreme debris disk targets with the goal of really trying to actually get at their spectral slopes, which gets at something about their grain size distribution and their collisional properties, and to also try and search for cold outer counterparts to these sort of like inner extreme hot disks, right, that are showing these massive collisions and these transiting objects, but to actually look for belts that are colder and further out. And just to kind of highlight another individual system here, right? So this is RZ Pisces, and what's neat is that in this system, we were able to model the exocomets and actually trace the larger end of the grain size distribution. So this is showing the RZ Pisces in the green and blue points, the actual sizes and numbers of comets, so number of comets as a function of size. And so we're really tracing the sort of like 10 to 1 kilometer range of size. But by then moving out into the far infrared, we could, continue expanding the size distribution. And this is exciting because we can actually now, with such a widespread in size, compare it to our own solar system. We can compare it to interstellar objects. So we're really starting to put this into context. Okay, and then Nick Ballering led a case looking at mineralogy of debris disks. So using the FIRES mode to target things like olivine, which has a feature at 69 microns. So, there's many features in the far infrared of things like olivine and pyroxene silicates, and those actually let you get at both the crystallinity of the dust and things like the iron to magnesium ratio. So these are simulations that Nick made showing, changes in iron percentages and crystallinity, and you can actually see this, noticeable change in the spectrum. And this was combined with also doing the same sorts of studies for protoplanetary disks, basically to try and look at the mineralogy of more evolved disks and younger disks, and then be able to actually understand kind of what level of grain alteration has happened during the planet formation phase. And just to highlight, kind of the current state of the art again, Beta PIC is probably one of the few systems where this has been looked at and was able to be done with Herschel. So both Spitzer and Herschel detected olivine crystals in Beta PIC in these sorts of spectra down here. And intriguingly, they showed similar composition to kind of the more primitive Kuiper belt objects. But, this has been done for Beta PIC and not many other systems. So with PRIMA, we'd be able to do this for many evolutionary stages of disks and on a much, much larger population. So hopefully that gave you a sense or a little bit of a whirlwind tour of like what we could do in debris disks. PRIMA will give us completely new insights into all stages of planet formation. I focused on debris disks here, but other PCAST talks on protoplanetary disks, younger disks. With the high resolution and low resolution spectroscopy modes of FIRES, we'll be able to do a number of things like tracing volatile species like water and O1 and C2, and also solid state species like olivine and water ice, and really look at the chemistry and the processing of these reservoirs for planet formation. And Primager allows us to do these sorts of deep surveys that will detect new disks and then be able to actually place our own solar system into context. So, for our working group, we have these 9 cases. There are 44 cases that are just generally related to the ISM star and planet formation in GeoBook Volume 2. And we're using basically all the different modes of PRIMA. So it would be really exciting to actually get this data. So I then was going to take an abrupt turn and talk about the PRIMA Internship Program. I could pause for questions on debris disks now or keep going. I don't know, Betsy, if you have a preference on that.
Either is fine. Please do whatever you would prefer.
Okay. Well, why don't I just go through the internship program and then I can stop sharing and actually see everybody's faces again, and we can have Q&A about everything. So I have been pretty deeply involved for the last, I don't know, however long the CSR has been developed, in helping create a student collaboration for PRIMA. And that student collaboration is what we're calling the PRIMA Internship Program, or PIP. And the goal here was really, I noticed that there are a number of programs existing to try and train students on how to participate in NASA mission development, but they are all mostly abstract, and they do not give students a chance to contribute to an actually selected flight program. So the goal here was really to fill that gap, to create a program that allows early career scientists to actually get involved in like a real-time look at how missions are developed. So what this is a 10-week summer internship program that would start during Phase B and run all the way through launch for the mission. This calendar here is showing you kind of how those 10 weeks are divided. The first week is really devoted to sort of like orientation and getting students, what's happening. Then the next 3 weeks are actually shadowing. So a key part of this is that we want students to actually experience sort of all the different pieces that go into a mission, both the science and the engineering and the management side of things. And so here, students will actually be paired with a mentor and do a 1 week rotation in each of those 3 areas. And then at the end of that, end of the 4th week, they'll sort of pick whichever they're most interested in and then do a dedicated kind of more in-depth internship for the remaining 6 weeks of the program. There's also kind of a course part of this. So that's what's highlighted here is there will be like lectures on Monday and Wednesday where they actually learn about some of the other things that aren't, part of what they're doing in their internships. So things like, how do you actually write a science traceability matrix and, how are missions classed and things like this. This is a program that, I am showing here as the director of this, but really there's a whole team that was involved in this. So we have site coordinators because we run in parallel at both JPL and Goddard. So at JPL, Tiffany Kataria is the lead, and at Goddard, it's Tom Eschinger-Heilman. And then Kara Barasby is the associate director. And, key part of this is that we want to make sure we actually do something effective. And so we have partnered with NORC to actually do an entire evaluation of the program throughout the whole program duration. So NORC is at the University of Chicago, and they are sort of an independent organization that actually, works in education research. Just to highlight kind of how the thought has gone into that, and that we've actually crafted basically a set of learning objectives and a matrix basically of like how every activity in the program maps to those learning objectives and what we want interns and mentors to take away from being part of this and what the outcomes are and how we will actually evaluate based on that. To give you an idea of sort of, we've gone down into like what a day in the life of a student looks like and how we sort of balance all of these different parts of the program. You imagine a student has some part of the day actually, doing lecture content, doing hands-on activities, having time to cohort with their group of students, really trying to integrate them into all parts of the mission so they get a real sense of how this functions. And one of the cool things that we've leveraged here is that there's actually been a number of interns who've been involved with PRIMA during Phase A, when we don't even have this program already. So here's just 3 examples of interns that have been involved in all parts of this, from doing kind of management to science and to engineering work for PRIMA. And so my kind of takeaway here was that, the goal of this program is essentially these 5 things. These are what we want the interns who participate in this program to, take away from this, to really like have a sense of how NASA missions are envisioned, created, developed, and what the different roles on a mission are, and to really be able to like see themselves taking on those roles in the future. So to hopefully, use the PRIMA mission as an opportunity to kind of demystify the entire process of mission development and really involve early career scientists. Okay, so with that, I am going to stop sharing. And I'm happy to take questions on any and all of that.
Thanks so much, Meredith. Folks can add questions in the chat or just go ahead and unmute and ask. Can you say a little more about poem targets and the timing of that, and so how that might be sort of used to help maybe design sort of the most optimal PRIMA follow-up or targeting?
Yeah, so POEM was selected as part of the Pioneers call for NASA. So it has a 5-year timeline from basically selection, which was last year, to launch. It will fly as an Antarctic balloon mission from McMurdo. So we're targeting roughly like 20 days, up to maybe 30 days of actual observations. So, that means that the goal is to look at a number of sources, but, probably a sample of maybe 10 debris disks. So, and then with an extra attention on beta pic to really do this kind of detailed analysis. So it will launch sooner, right? We're aiming for like 2029. So we'll be able to get the data in advance of PRIMA, and for a smaller sample. So to really be able to fully do the analysis and like inform then target selection later for PRIMA.
But that definitely means like these are all targets that should ideally be able to follow up with.
Yes,
with
absolutely. Yeah, yeah. Right. So I mean, we're picking in the same sort of way. So like we're picking debris disks and protoplanetary disks that have been observed with ALMA and have, dust and gas measurements, and that we can, we'll just be able to look at more of them with PRIMA.
Muted myself. All right. So if there are no other questions, I want to go ahead and just thank Meredith for such a informative and wonderful talk, and encourage folks to tune in again next month, when we will be hearing about polarization from Susan Clark. So thank you again, Meredith.
Yeah. Thanks for having me, Betsy.